and also would like to share the screen. Okay, so firstly, let's go to the slide in order to explain the content of the first exercise of the homework, which, as you already know, is part of the exam evaluation. So it's the second homework that we will use as part of the exam evaluation. Basically, the homework consists in a beam, a continuous beam with 3 span, where the intermediate support are supported by 2 vertical columns. This is basically a simple scheme for example, a continuous bridge or a continuous footbridge. And in fact, let's look at the different dimension. Okay, so we have that the central span is 1.2 times L, with the dimension L being equal to 20 meters for all. Okay. In addition, all the 3 spans are supported by an uniformly distributed loads equal to 4 kilonewton per meter. The height of the column is 10 meters, and we have also that the central span is subjected to another uniformly distributed loads whose value is equal to alpha kilonewton per meter. And as usual, alpha depends on the first letter of your first name. So alpha will be, for example, 11 if the first letter of your first name is A, B, C, D, E, while alpha will be equal to 15, for example, if the last letter of your first name is U, V, W, X, Y, or Z. Okay? Okay, I would like to ask you to solve these exercises in 2 parts. First of all, let's look at the continuous beam without considering the effect of the columns. Okay, so we are basically in this part of the exercise, we are basically assuming that the columns are indefinitely stiff in the axial sense. Okay, of course, this structure is 2 times redundant, and so the first thing I would like to ask you is to solve this redundant structure by using the force method. And of course, once you have solved this redundant structure by using the force method, you can compute the reaction, the shear diagrams, and the bending moment diagram. Okay, after having done so, you have to choose the beam cross section, assuming that the class of the steel is an S235, so that the maximum bending moment does not exceed the yielding bending moment of the beam cross section you have chosen. Okay, afterwards, since at this point you have shear and bending moment which are numerical value. For example, the shear value corresponding to this intermediate support will be equal to 22 kilonewton per meter. Okay, it is possible to verify your computation in terms of bending moment and shear force by using the code Telaio 2D. Okay, once having doing this, we know also the value of the reaction acting on the intermediate support. But now let us assume that the reaction in the intermediate support is the axial force of the 2 columns, because we have to remember that the original structure also includes 2 columns that are the supports to the intermediate sliding element. Okay, so I would like that you choose the cross section of these two columns so that the backlink verification is verified according to a stability curve number A, and assuming that the class of the steel is S235. Basically, you have to ensure that the value of the normal stress should be less than or equal to K, which is function of the slenderness, over the value of Fy, the yielding stress, over the gamma M1, which is the safety factor. In order to apply this formula, in order to apply this strengthening verification, this stability verification, I would like to remember you that you have to evaluate the slenderness. But in order to evaluate the slenderness, you need to evaluate the effective length of the column, and the effective length of the columns depends on the constraint condition at the base and at the top of the column, basically. And of course, you need to know which is the cross section, because you need to know which is the radius of inertia of the cross section, because the slenderness is the ratio between the effective length and the inertia radius. Okay, so in order to force you to be a little bit more motivated in solving this exercise, I will add a bonus. So if the part of the exercise that are denoted as 1 and 2 are solved also using the displacement method, you will have a bonus of 2 points in the final mark of the exam. So this means, for example, that if your overall mark, by considering the effect of all the exercises, of all the homework, and the effect of your oral exam is 22, if you can count on the bonus on this exercise, you will have a mark not of 22 but of 24. Of course, from academic standpoint, what is interesting from our point of view is that basically you have an exercise consisting basically of a continuous beam, and you have to solve this exercise by using the first method, the displacement method, and by also using a computer code, the computer code Telaio 2D. Okay, of course, there is a time schedule for delivering these exercises, this series of exercises. This homework should be sent by December 12, so basically you have a little bit more than 2 weeks, and you have to send the worked exercise as a PDF file both to myself and to Antonello Ruccolo. Okay, as usual, in order to allow us to classify and order your exercise, I kindly ask to call the exercise as SD02. So SD, Structural Design 02, second homework. Afterwards, we have to put the last name and your first name, and you have to send us a PDF file. Okay, good. After having explained this, I would like to go back just for one moment to the list of the participants, because the list of the participants increased a little bit with respect to the beginning of my talk, and I would like also to ask Dr. Ruccolo to get a look to the list of the participants, because also Dr. Ruccolo can admit the participant if some new participant is joining us and is asking to be admitted in the virtual room. Okay, after having doing this, I would like to share again my screen, okay, and to go back to the content of the class of today. As I have anticipated, the second aspect to be discussed in the lecture of today is how it is possible to design the connection between a column and a foundation. Generally, this kind of connection consists of one plate. The plate is connected by welding to the columns, but also this plate is resting on a reinforced concrete block, and the connection is generally completed by some long bolts that are connected to the foundation block, and there are also some plates that are steel plates that are orthogonal to the main steel plates. Of course, the behavior of this kind of connection strongly depends on the eccentricity of the axial force. Because if we have an axial force with no eccentricity, so an axial force passing for the center of the connecting plate in plan. Of course, these long bolts does not work. That's not work because we use the stiffness of this plate in order to distribute the effect of the applied axial force in contact pressure between the plates, the bottom part of the plates, and the foundation block. So if the axial force is centered, we have an uniform distribution of pressures on the concrete block, okay? Of course, the contact stress, the uniform distribution of pressures is easily evaluated because it's simply equal to the ratio between the acting force N and the area of the contact force, okay? If we have a small eccentricity of the axial force, of the force that is transferred by the column, of course, still we have a distribution of contact pressures under the plate. But as you can see in the central scheme, this distribution of pressure is no more a constant distribution of pressure, because as usual, we have a larger pressure on the right hand side and a lower pressure on the left hand side, because we have to superimpose the effect of an axial force which is placed, which is acting in the center of the plate. But in addition, we have also a bending moment, and the value of the bending moment is N times the eccentricity E, okay? And so, of course, a bending moment will induce a linear distribution of contact pressure. Why? Because we are basically assuming that the steel plate can rotate, but it preserves its plane behavior. If the plate is rotating but it remains plane, it means that we have larger stresses, larger contact stresses on the right hand side and lower contact stresses on the left hand side. Of course, when the eccentricity exceeded the the inertia, what is called in Italian nocciolo di inerzia of the cross section. So if it exceeds this distance, and this distance is equal to the overall 8/6, if we would like to look at this dimension, this dimension will be equal to h/3. If the eccentricity exceeds h/6, then I have that we will have a quite high bending moment. The quite high bending moment is still equal to the product between the axial force and the eccentricity. But now what's happening? The plate continues to rotate by remaining plane. But this part of the plate now is no more in contact with the block of reinforced concrete. And so the effect of this long bolt is giving a vertical force, substituting these tension forces, these tension contact stresses that are not possible in a contact problem. Okay, so by looking at the mechanical behavior of a connection between column and foundation in terms of eccentricity, we can summarize this mechanical behavior by saying that in the case we have no eccentricity, or the eccentricity is quite low, basically there is a transfer of the axial force and of the bending moment through just contact pressure between the plate, the steel plate, and the block in reinforced concrete. Okay, so in this case, the long steel bolts are acting as mounting elements. Okay, they are basically not working. If they are working not for axial force or for bending, but they are working, for example, in order to resist shear. Okay, otherwise, if we are dealing with a case in which the eccentricity is quite large, okay, now these bolts are useful because they have to support also an axial tension force. Okay, of course, when we are dealing with a column beyond the centered or not centered axial force, okay, there is generally at the base of a column also the presence of a shear force. In order to transfer the shear force, we have basically two possibilities. First of all, we can use the bolts. Okay, so for example, if we have 4 bolts connecting the plate with the foundation block, this shear force divides in 4 times one equal part for one of the 4 corner long blocks, long bolts. Otherwise, it is possible to have a welded plate in this position, and then we can use the contact between the concrete and this plate in order to transfer the shear force to the concrete block. So since the upper plate and the vertical plate are a stiff body, okay, the shear force T is pushing this rigid body against the concrete. And if there is this push against concrete, there is also a uniform distribution of horizontal stresses, okay? And so the shear force in this case might be transferred not by using the bolts, but using this vertical plate, okay? Good. Afterwards, of course, we have to make the strength verification of all plates depending on the distribution of acting pressures. For example, if we have this kind of plate, okay, with a vertical plate, let's look at the vertical plate. The vertical plate is subjected to a uniform distribution of horizontal normal stresses. The value of sigma t of this horizontal normal stresses is very easily evaluated because it's the ratio between the acting shear T and the area of this plate, okay? And so we can basically verify the vertical plate as it behaves like a vertical cantilever beam, okay? Otherwise, if we are going to look, for example, at the upper plate, the upper plate, for example, is subjected to a triangular distribution of stresses, the one denoted here as sigma and m, which means the sigma, the normal stresses associated to the action of the axial force and of the bending moment. And remember that this bending moment will be equal to m times the eccentricity E. Okay, so we have this uniform triangular distribution of vertical stress, and of course we will have two tension forces in the bolt. And so if we look at the right hand side of the horizontal plates, it behaves basically as a cantilever beam under the action of this triangular shape of pressures. Otherwise, if we look at the left hand side, the left hand side behaves again as a cantilever beam, but now the cantilever beam is subjected to the action of these two forces NB, which are the forces in the two bolts. Okay? If we want to solve for the contact pressure induced by the action of the vertical acting force and by the bending moment, we have basically two possibilities. A correct solution, which is directly correlated to the assumption that, as usual, the plate rotate remaining plane. Otherwise, I can also use an approximate solution. So instead of saying that these horizontal plates rotates remaining plane, we can say that the distribution of the vertical stresses is a uniform distribution sigma and m, okay? Not a distribution according to a triangular law. No, a uniform distribution. In addition, if the width, the overall width of the plates is denoted as capital B, we can state that the dimension of this compressed part is equal to 1/4 of capital B. Now, it's obvious that what we do not know in the case of the correct solution, as well as in the case of approximate solution, are the value of the contact pressure, sigma and m, in the lower case, but also in the upper case. And also, of course, the value of the force acting in the bolt. In order to evaluate these two unknown, of course, I would like to use the equilibrium equations. In fact, two equilibrium equations are available. The first one is the equilibrium equation with respect to rotation. For example, to rotation around this point, okay? If I use this kind of equation, I can find directly one of the two solutions. The other one is, of course, the overall equilibrium condition in the vertical direction, and hence I can obtain also the axial force. But this holds in the case of approximate solution. Why? Because in the case of approximate solution, I have made the assumption that the dimension of the compressed region is equal to capital B over 4. But in the general case, when we are dealing with a rotation of the upper plate, we do not know which is this distance, okay? Which is the position of the neutral axis. And so we will have basically a third unknown to be evaluated. Since we need to find a third unknown, we also need a third equation, a third condition. And the third condition is directly supported by the fact that our plate is assumed to rotate according to a rigid body motion. So it rotates by remaining plane. If it rotates by remaining plane, it means that the stress in the contact concrete will be proportional to the Young's modulus of the concrete. But also the stress in the bolt will be proportional to the Young modulus in the steel, because the bolt is made of steel. And we know that the Young's modulus of the steel sorry, is much larger than the Young's modulus of the reinforced concrete. So basically, we have to introduce also the ratio between the Young's modulus of the steel and the Young's modulus of the concrete. Okay, so first of all, let's try to solve this problem, this contact problem, by adopting an approximate solution and by using only equilibrium equations. We have already stated that here the main key is assuming the dimension of the compressed region. Okay, so if the overall length of the plate is capital B, we can assume, for example, that the width of the compressed region is B over 4. Okay, at this point, if I make an equilibrium to rotation around this point, okay, the resultant of the contact pressure at the interface does not act in the equilibrium, in this equilibrium equation. So in the equilibrium equation, we will have only the action of the axial force, and the distance of the axial force from the center of this compressed region is well known because we know the geometry of the problem, okay? We know the eccentricity, and so we know where is the position of the force capital N. So the bending moment with respect to this point of the force capital N is capital N times B. This bending moment should be equilibrated by the moment associated to the tension in the bolts. So number of the bolts times the axial force in the bolts times, of course, this distance. And this distance, for example, is denoted as A. So it is possible to evaluate from this equilibrium equation, it is possible to evaluate very soon the value of the vertical tension in the two bolts as ratio between this product N times B and this other product, the number of the bolts, in this case it's 2, times this distance A. Okay, perfect. Afterwards, since now I know N, I know also the value of N in the bolts. The only thing that is still unknown is this value of the contact pressure. And so I would like to multiply this unknown value times the geometry of the contact region, and the geometry of the contact region is this dimension, P over 4, times the dimension in the direction orthogonal to our drawing. So A times P over 4 equal to the summation of the two axial forces, N, and the number of bolts times NB. And so in this case, it's very easy to evaluate the value both of the N, capital NB, and of the contact pressure, sigma and M. Okay? So by using the equilibrium equation, it is very easy doing this. Okay? Now, the solution in the other case, in the case in which we use the correct solution, is a little less simple, because we have to use basically three conditions. The first condition is the one involving the rotation, the stiff rotation of the plate. And when I use this kind of property, I have to remember that there is one more unknown, and this one more unknown is the distance between this point, this axis, and the border of our plate. So we have, first of all, this dimension which is unknown. On the other hand, if I assume that the plates rotate remaining plane, it will be that the distribution of the contact stress, it will be a linearly varying distribution of stresses. And this depends, of course, on the linearity between stresses and strain. The plate is rotating, remaining plane, so the vertical deflection is 0 along this axis, but it increases when we move from this axis across along until the border of the plate. And so since we have an increasing deflection, I will have also a linearly increasing contact stress. On the other side, we have that also there will be a vertical deflection, which is directed upward, and also this deflection depends on the distance from the neutral axis. And so if also these elements depend on the distance from the neutral axis, also in this case, by assuming elastic behavior of the steel in the bolt, we will have that there will be a linearity between the stress in the bolt and the deflection. But of course, putting everything together involve, in order to obtain basically the solution in terms of X, the solving of a third degree equation. So let's look at the analytical form of the equation. We have x cubed, and x is this distance, the distance of the neutral axis from the border of the plate, plus a term that it's equal to 3 times E minus capital B over 2 times x squared. X squared is again, x is again this distance. E is the eccentricity. So the ratio between the bending moment and the axial force. Capital B is the dimension of the plate in this direction, okay? Is the overall width of the plate, plus 6 times M times AF over A times D times X. Okay, X is, as usual, this distance, okay? AF is the area, the steel area of the two bolts, okay? M is the ratio between the Young's modulus of the steel and the Young's modulus of the concrete. This coefficient will become very important in the analysis of reinforced concrete cross section, okay? In addition, A is the area of the plate, okay, of the contact plate. So it is equal to, not the area, but this dimension, the width of the plate, okay? So we have the width of the plate in this direction that is denoted, as you can see from the drawing, as capital B. The dimension of the plate in this direction is capital A, and this is again capital A. In addition, we have basically, I have explained everything, not everything, because we have also this distance D, but this distance D is the distance between this alignment of the bolts until the vertical alignments of the axial force. So D is exactly this distance, okay? The last term is again 6M times the ratio AF over A times D times H, okay? Perfect. this is, of course, a third order equation, basically. How it is possible to solve a third order equation? By using, for example, Excel. Okay, for example, we can assume that x is equal, for example, to capital B over 4. So if you put capital B over 4 cube, capital B over 4 square, capital B in this term, of course, if I am very lucky and capital B over 4, so in my first trial, is the right solution, I will obtain that the summation of those terms, the first two are positive and the second two are negative, will be effectively equal to 0. Otherwise, I have to try again, okay? But how to try again? Basically, we try again if in this way, if this summation gives a number that is larger than 0, I have to decrease the value, the trial value of x. If it gives a value that is lower than 0, I have to increase it. Of course, generally in a couple of iterations, 3 or 4 iterations, I can find the right solution, because I can very easily find the right solution when I obtain a solution when the trial value gives an overall value in this equation that one time is larger than 0 and in the other side is lower than 0. Generally, it is generally very useful obtain the real solution by making an average between the two, or a weighted average between the two. But once I have evaluated the position of x, of the neutral axis, of course, I have also to evaluate the value of the contact stresses at the interface with the concrete, and of course I have also to obtain the value of the stress in the steel. Okay, in order to obtain the value of the normal stress in the contact surface, I can use this equation. So at the denominator we have the axial force capital N. At the denominator we have capital A times x over 2 minus h minus x times m times the ratio between AF and x. If I want the stress in the steel of the bolt, I will use this kind of solution. Basically, let's look that it is obtained by a simple formula using the similar triangles. The only novelty with the classical formula, with the similarity between triangles, is this coefficient m. Okay, and so by multiplying the value of the stress in the bolt by the area of the bolt and dividing by the number of the bolt, I will obtain the resulting tension force in each one of the bolts. So basically it's a little bit tricky, but remembering these equations that are quite easy, it's not so much difficult to solve this kind of solution. If you want to try to make some computation by your own, you can, for example, use this geometric characteristic of a real connection between a column and a foundation. Of course, here I have proposed basically two different couple of axial forces and bending moment. In the first case, of course, we are in case of lower eccentricity, while in the second case, we are in the case of a larger eccentricity. And for example, you can use this geometry and the value of this number in order to solve these two simple cases by using what we have shown in the simple case of lower eccentricity, of low eccentricity, and in the more general case of large eccentricity by applying a correct solution or an approximate solution. Okay? Good. Now I would like to change completely the topic of my talk, and I would like to talk a little about seismic hazard and the seismic response of structure. But of course, before doing this, I would like to stop just a moment the sharing, okay? And I would like to ask to the audience if there are some comments, some questions. Is everything is more or less clear? Okay, I would like to ask a question to the audience. If I have to choose to evaluate the stresses under the connection between a column and the foundation, and I'm quite free to choose between the approximate solution and the correct solution in the case of large eccentricity, which one of the two you will choose at the beginning? So please try to give me an answer, the approximate one or the correct one. Please. I do not see any reply in the chat, and I cannot see any comment. Please. For example, Mrs. Greta Pecchi, can you ask to my question? Have you understood it? Guys, are you present? Are you there? Can you hear me?
Yes, we can hear.
Okay, you can hear me. I have given a question. I repeat the question. If you are free to choose between the approximate solution and the correct solution, which one you apply first? If I have to choose, generally, I prefer to apply first the simpler solution. Which is the simpler solution? Please repeat.
The approximate solution.
The approximate solution is, of course, the simpler solution. So if I'd like to make some quick computation, the first thing to do is to apply the approximate solution. Afterwards, if I want to refine my computation, I can also use the correct solution. But the interesting aspect is generally that when we generally apply the approximate solution and we obtain, for example, not correct response from this simple computation, it simply means that the dimension of the contact plates are too low, and so I have to increase the dimension of the contact plate. When the approximate solution gives to me a satisfactory solution in terms of stress at the concrete interface and stress in the steel, generally it means that also the correct solution will give a satisfactory solution, basically, and so my initial choice of the plate is the right one. Okay. Let's go back to sharing the video. Okay. And the objective of this third part of my presentation is talking a little bit of the seismic hazard and about the response of structure to earthquakes. Okay, basically, the mechanism generating an earthquake is usually referred to the presence of some active faults. When we have active faults like this one in red in the underground, what happens is that when there is a lot of energy present, for example, in some part of this fault, there is a sliding between the different part of the faults. And this kind of sliding generate a very strong vibration in the ground that propagates for kilometers and kilometers. Of course, at present, we know very well, not only in Europe, but all over the world, which is the position of the important active fault. So, for example, every one of us knows very well that one of the most important fault in the world is placed in California. And that fault, the name of that fault is Sant'Andreas fault. But also in Italy, we have a very important fault that is practically crossing all our Apennine, so along this line. And in fact, in recent year, we have had basically strong earthquake in central Italy, whereas we remember some very high earthquake in the region of Friuli, for example, in the 70s. Of course, the map of seismicity is changing in time because as decades are passing, we know in a better way which is the behavior of those faults. In addition, at present there are a lot of seismometer networks which are distributed along the world, and so we can very easily record also the amplitude of the different earthquakes. For example, in Italy, we have a very large seismic network. So, for example, if we are going to the map to look at the map of seismic hazard from the 70s until the 80s, until the beginning of the year 2000, you can see that the red and the orange region in this map are changing. Okay. But if we want to obtain a quantity, just one number, giving to us a reasonable measure of the seismic hazard, generally we refer to the so-called AG. The AG is defined as the horizontal peak ground acceleration on free field and firm ground. What does it mean? First of all, of course, it's a peak horizontal acceleration. So it's the maximum acceleration measured or expected at a certain site. Okay. In addition, of course, the acceleration of the ground is changing because, for example, it is different near the fault or at 30 kilometers far from the fault. And in addition, is different if we are measuring this kind of acceleration on the ground, on the free surface of the ground, or we are measuring this acceleration at depth, for example, or of 1 kilometer near the fault in the ground, inside the ground. Okay, and in addition, there are also some differences in acceleration if we are measuring that acceleration on the rock, or for example, if we are measuring it on a soft ground. Okay, so generally, when we talk of this value of Ag, this value of Ag in many cases is an ideal value, which is obtained from the knowledge of the seismicity of a region. It's an horizontal acceleration, and we are going to refer to a maximum acceleration. In addition, it is in condition of free field. Free field means the surface of the ground. But in addition, the surface of the ground in free condition. What does it mean, free condition? Far from buildings. For example, if there is a large garden around our building, basically we define the horizontal ground acceleration in the free field, which means in the garden, not very close to the building. Okay. In addition, we have to assume that the ground is rock. Okay. And of course, the free surface is not generally rock. For example, the free surface might be constituted by a soft soil. So, for example, what we do in the practice is that we have practically in a continuous dependence on the geographical coordinate. We have a continuous mapping of the horizontal ground acceleration on free field and firm ground. But if my building is not in free field and not in firm ground, I can pass from the value given by the code to the effective value, the effective design value of my building by amplifying it for some appropriate coefficient. Okay. In addition, we have to consider different aspects. Of course, if we are going to assume the location of our building to be designed, of course, in that place, I can expect medium or low earthquake, but I can expect, of course, also very large earthquake. For example, in Sicily, in Calabria, in Friuli, in Abruzzi, we have to expect also very large earthquake. So what we have to expect is that a generic building for sure undergo a quite medium earthquake, and for a quite medium earthquake, basically I would like to maintain the behavior of the building in the elastic range. But if I'm not lucky, during the lifetime of the building, for example, during a scheduled lifetime of 50 years, of 100 years, that building might experience also the largest earthquake expected in that site. And so, in that case, I will undergo to the largest earthquake, but also using the inelastic behavior of the building. So I also accept significant damage to the building, but without loss of lives. Okay? So basically, every building might be designed, should be designed in order to undergo in the elastic range to a medium level earthquake, okay? And of course, to this medium amplitude earthquake, we have a seismic hazard associated and also a different risk associated. Different with respect to the largest expected earthquake in that site. In this case, in this second case, we can accept severe damage of the building in the plastic range, but no loss of lives. But if we continue our talk and let us think to the response of the buildings, we have to consider another aspect, because of course the response of a building to an earthquake depends for sure on the location in which the building is installed, is built, okay? Because depends on the seismicity, on the seismic hazard of that site. Okay, but in order to solve the problem of building a certain structure, I can use a steel structure, a steel composite structure, just a steel structure. I can use also, for example, wooden structure. I can use different solution in terms of materials and in terms of characteristics of my buildings. So, since there are a lot of parameters that are affecting the structural behavior of a building, I can expect that some of these parameters also affect the seismic response of a structure or of a building. And in order to begin to understand this, let's start from what we can measure in real building by using, for example, an outstanding building. Okay, this is the Trans Am building in San Francisco, California. One first aspect that we have to expect is that some part of the structure is subjected to an acceleration, okay? And that part of our structure is characterized by a mass, okay? And everything is characterized by a mass. We know, basically, that everything has weight. And so our weight is proportional to the mass, or if you prefer, the mass is proportional to the weight, okay? Or if you want, the mass is the weight divided the acceleration of gravity. But generally, we have that the product of a mass by an acceleration generates a force. This is called inertia force. We can experience every day the inertia forces. For example, when we are traveling in our car, generally our body is not subjected to any horizontal forces if we are traveling at a constant velocity. But when our velocity is changing because our motion is accelerating or decelerating, we can clearly feel some forces. For example, if we increase our velocity and so produce a positive acceleration, we can feel a force pushing ourselves in this direction, in the direction of the motion. Otherwise, if the velocity is decreasing, so we produce a negative acceleration, there is a force in our car pushing ourselves against the seat. Okay, so if we are decreasing in this direction, if we are increasing in the opposite direction, okay, so increase of acceleration, we are pushed against the seat. If we are decelerating, we are pushing in the front direction. This is very typical when we are going to brake. So we have inertia forces which are proportional to the change in the velocity. But the change in the velocity is an acceleration. Okay, but let's see how the acceleration is changing in a real building or even if in a cantilever structure. And for example, it is possible to measure the acceleration during an earthquake by installing some sensors that are measuring the acceleration. These sensors are called accelerometers. And so, for example, in an instrumented building, it's quite typical to measure the acceleration at the foundation level, the acceleration at an intermediate level, and the acceleration, for example, at an upper level. And if we are going to do this for the Trans Am building, for the Trans Am skyscraper in San Francisco, we discovered that the acceleration is increasing with the distance from the basement, okay? And so if the structural acceleration is increasing with the distance from the basement, since we have that the inertia forces are proportional to the external acceleration, then we have to expect that during an earthquake, the inertia forces representing the external forces are increasing from the basement to the upper floors. So we can quite easily understand that for us it is very important to know the seismic hazard in terms of acceleration of the ground, of acceleration at the basement of the structure. But we know that if we are looking at the response of our building, we know that the response at the upper floors in terms of acceleration will be much higher than AG. And so we have to expect something like this, an increasing distribution of forces, so passing from the lower level to the upper level. So what we expect is that the seismic loads increase with increased height or increased distance of the actual floor from the foundation level. Okay, perfect. But of course, we do not know how different will be the acceleration at the upper floor from the acceleration at the basement. Okay, perfect. Indeed, it is possible to establish which kind of amplification we have along the height of the building by knowing the seismic behavior of the building. In general terms, we can approximate the applied force at the different level of a building as the product of a certain acceleration times the mass. Okay, so for example, if we have that most of the mass at the first, second, third floor is proportional to the mass of the floor, because basically the mass, most of the mass is concentrated at the level of the floor. We can obtain the force by multiplying an acceleration by the mass of the floor. But that acceleration depends on AG, but it is not equal to AG. Okay? This kind of acceleration basically depends on the structural characteristics of the building. And we can very easily understand that the amplification or the acting forces are depending on the characteristics of the structure. This might be very easily evaluated in the practice if we are considering, for example, the same site. You can consider a certain town in Italy, okay, and a series of different buildings which are placed in the same site, along the same street. For example, we can assume that along the same street we have a very stiff building, which means a building with only 2 stories. So a more deformable buildings from 6 stories up to 20 stories, and a very deformable building, okay? For example, with the number of stories which is larger than 20. Okay, when an earthquake arrives, so this means that the ground of all this building is shaken by using the same natural phenomenon, the same acceleration. Okay, the same acceleration. We can observe that under that kind of earthquake, we will not have the same degree of damage for the all buildings. But for example, if this picture is related to a certain town, which is Mexico City, and to the earthquake measured in Mexico City in 1985. Only the medium stiffness buildings are subjected to major damage, whereas the upper building does not undergo damage, and also the lower building does not undergo damage. So this means that there is a strong effect of the characteristic of the building in order to make amplification of the seismic motion, to make this kind of amplification from the ground until the upper building of the floor. Okay, perfect. So once we have understood which is the conceptual basis, of course we have to understand which are the mechanism and the parameters affecting the seismic response of the structure. So an interesting aspect is, of course, that the height is important, but it doesn't explain what is observed in many post-earthquake assessment. So it is not only the height, but also the structural behavior of the building in terms of mass and of stiffness. And in fact, I would like to show you some qualitative results now. Okay, in order to do this, I will try to show you some movies. Okay, let's see. I'm trying to sharing those movies. No, not this one. The first one is not this one. The first one in my ideas, this. Okay, let's see. No, I don't want to make the movie start. Okay, I'll try to show you in full screen. Are you seeing in full screen now?
Not in full screen, but we can see. Yeah.
Okay, not in full screen, but it means that it's larger than before. It's larger than before or not?
Yes.
Okay, perfect. So what we can see is a very simple experiment. So which is the meaning of this experiment? I'm showing you 3 models of 3 different buildings. Okay, these 3 models of these 3 different buildings are basically different for the stiffness, because you can see every one of those elements consists of a certain mass, okay, and the mass is subjected to the ground, to this plate, basically by using, in the first case, some vertical columns exhibiting a certain height. In the second case, we have a more deformable, okay, element, because the height is larger. And in the third case, we still have, again, a more deformable element. You remember the concept of stiffness. We have shown during the past lecture that if we apply a unit displacement to a clamped column, we obtain a shear force that will be equal to 12 EJ over the cube of the height. So the higher the height, which is its denominator, the lower the stiffness. Okay, the lower the height, the higher the stiffness. So what I expect is that this system is more deformable than this one, that is in turn more deformable than the first one. So the lower one is the stiffer, the upper one is the more deformable. Okay, now let's try to make this kind of experiment. Let's apply at the base of this system an applied motion. The applied motion is very simple. It's just a sinusoidal motion. But we are going to increase the frequency of the motion, okay? Perfect. So let's see what happened when we are doing this. So you can see that now our basement is oscillating through a sinusoidal motion. And more or less, we can see that in the beginning, all the three masses are experiencing the same motion as the ground. So no appreciable deformation in this three system. Now let's see what happens when the frequency of the applied motion is increasing. Now we are seeing that the higher system is exhibiting larger deformation, and it is exhibiting also an amplification with respect to the motion of the basement, okay? So for example, we have a certain motion of the basement, and now we have an amplification in this motion. And we have also that there is a relative motion of the upper mass at the frequency you have seen of 4 Hertz. This is a resonance for this system. We have a very large amplification, so a very large apparent force, because we have a very large acceleration of these masses. Now, the frequency of the applied motion is decreasing, and is the second system now exhibiting a very high acceleration and an amplification, because now it's the stiffness of this second system which generates a second resonance at 6.35 Hertz. And so now we will see a very large acceleration and a very large displacement. But since this displacement is very large, it means that also the force generating that displacement is very large. Now, the frequency of the forcing function is still increasing, and now the upper two systems are not exhibiting a very large acceleration, but a very large acceleration is now exhibited by the stiffer element, okay? Now it's the stiffer element that is undergoing to very large acceleration, to large forces, and to large displacement, because now the frequency of the earthquake is very close to the resonance frequency of that system. And now we are exactly at the resonance of the system, 11.35 Hertz. And so this very simple experiment, sorry, I would like to go back. So, okay. This simple experiment shows to us something similar to what happens to three different buildings which are placed in the same site during an earthquake. Because generally an earthquake has a waveform, and the waveform basically is a clear frequency content. If the frequency content of my earthquake is very rich, as it happens, for example, in Mexico City earthquakes. For example, for the frequency of medium rise building, those kind of building will experience a large motion, basically, and they will also experience a quite large forces and deflection. But now, of course, we are comparing very simple structure with the real building. But this second movie I will show to you is aimed at showing you that what happens for a very simple system indeed also happened for a more complex system like this one. This one now, it's a simple model of a 3-story building. And we will repeat the previous experiment. So an earthquake, an artificial earthquake, will be applied to this more complex system, okay? And the artificial earthquake is given very simply by a sinusoidal motion with the frequency of the sinusoidal motion, which is very slowly increasing. So let's see what happened. Okay, now the movie has started, and so we have a low value of the frequency of the sinusoidal earthquake. Okay, we have reached the first resonance of the system. In fact, we can see a very significant amplification of the motion according to a deformed shape, which is the deformed shape of a clamped cantilever beam. Now the frequency is increasing, and very soon we will obtain a new resonance for a larger frequency. Now the frequency is increasing of the applied motion, and we also begin to see some deformation, some displacement of, for example, the lower mass and the upper mass, whereas the intermediate mass is almost not moving. Okay? So increasing of the deflection at the lower level and at the upper level, with the intermediate mass approximately not moving or oscillating with the blades. This second resonance is at more than 12 Hertz. Okay? Of course, if we are going to increase the frequency of the applied motion at the basement, we will reach a further resonance. Okay? So I will try to resume also this one. Okay? But I would like also to show a new kind of simulation. Okay, what we have seen basically in our movies. Basically, in these movies, we have understood why when we have 3 different buildings in a row in a real street, maybe not every building undergoes exactly the same kind of amplification and the same kind of damage. Okay? Why? Because the mass and the stiffness of the building basically are related to something I have called as resonant frequency. Okay? And in addition, we have seen that if we are dealing to systems that are more complex than a simple mass which is connected to the ground by a spring. Also, when we are dealing with the complex systems, we have the possibility of having several resonances. In addition, we have seen that there is an important effect of the spring, of the stiffness of the spring on the resonant frequency. But of course, I will show now that there are also other effects, like the mass or the dissipation of energy. Okay, first of all, let's apply a mass. So let us denote a system which is characterized by a mass of 100 grams, okay, and a certain stiffness, okay. Let us suppose that we are starting from a deformed condition. And let's see what happens when I remove the applied displacement. What's happening? It's happening something similar to the first movie. We have generated an oscillation, and there is a frequency of this oscillation or a fundamental period of this oscillation. There is no dissipation of energy. So basically we have that the same motion will continue indefinitely, okay, with a certain value of the fundamental period or of a natural frequency. Now, what we have said? We have said that if the stiffness of the spring decreases, the frequency of this motion will decrease as well, okay? In addition, the fundamental period, which is the opposite of the frequency, will increase as well. So when I'm going here, I'm going to decrease, for example, the value of the spring constant. What I expect is that the fundamental periods will become larger. Let's do this. So now you see that the cycle up and down is lower than before, and so the fundamental period increases, and the frequency, the natural frequency, which is the opposite of the fundamental period, decreases. Now I would like to increase again the stiffness, and so now you see the velocity of the motion is larger. So the fundamental period decreased, the opposite of the fundamental period, which is the natural frequency, of course, increased. Okay, now let's stop this motion and let's change the mass. Okay, for example, okay, this is the fundamental period associated to this mass. Let's add, for example, a larger mass. What we see is that when the mass is larger, the velocity of the motion is slower. So the fundamental period is larger. Fundamental period is the time interval needed for obtaining two subsequent maxima value. Okay, so we have also understood which is the effect of the mass. So when we increase the stiffness, we can increase the fundamental frequency and decrease, of course, the fundamental period. The mass, the increase of the mass, have an opposite effect. When we are going to increase the value of the mass, the fundamental period is increasing and the frequency, the natural frequency, is decreasing. Of course, now we are dealing with a system in which there is no dissipation of energy. And in fact, what we are seeing in this kind of simulation is that the sinusoidal motion of our mass is happening with a certain natural frequency or with a certain fundamental period, but it continues in an indefinite way. Of course, in real systems, in real buildings, what we have a dissipation of energy. And so it means that it is not possible that this motion continues indefinitely. And in fact, now what I'm going to do is that I'm going to increase the damping. And so when we are going to increase the damping, you can observe what happens. So the motion is decreasing quite slowly. So the frequency of the motion is more or less the same, but now the system stopped. Okay, so I move it from the equilibrium position, and what's happening is that cycle after cycle, the amplitude of the motion is decreasing. So now we have effectively understood which are the effect of the structure on the response to an applied motion. We have basically that the stiffness and the mass are very important because the combination between masses and stiffness of the structure determines the fundamental period or the resonant frequency of the structure. And when an earthquake arrives, of course, the structure is excited mainly along its fundamental frequencies. So, for example, a nice choice is, for example, to build very deformable building on a rock soil and very stiff building on the sand, because if I build a deformable building on the rock, basically the motion of the rock is rich in high frequency, while a deformable building has a significant response for lower frequency. So there is a limited interaction between the structural behavior of the building and the content of the earthquakes. Conversely, if I'm going to build a very stiff building on a soft ground, the building tends to amplificate the higher frequency, but the soft soil tends to amplificate the lower frequency, and so there is a limited interaction between the two. Okay, after having shown this to you, and of course in the slide I will send to you, there are the internet address of this movie. The second one, the last one is the first one in this slide. We can basically conclude that if the mass and or the stiffness of this single degrees of freedom system, which is a tank, a real tank, when we have a real tank with the mass which is basically concentrated in the upper part, this is very similar. The behavior of this building are very similar to one of a single degrees of freedom system. So we expect that if the mass or the stiffness of the tank are changing, the dynamic and seismic response changes as well. Why? Because the resonant frequency or the fundamental period of the building are changing. In addition, of course, if I'm going to look at plate like this, if I'm installing the plate along the maximum stiffness plane or along the minimum stiffness plane, there is no difference in the material, but there is a very strong difference in the stiffness of the system. Because, of course, this stiffness is very large, while the second stiffness is not very large, while the mass is basically the same. And so the lateral forces will change their distribution. In addition, what we have seen? We have basically seen that a third parameters affecting the seismic response of structure is the capacity of dissipating energy. So for a linear structure, basically we can summarize that the dynamic and seismic response is dominated by three parameters. And those three parameters are the mass, the stiffness, and the damping. If we are assuming a small value of the dissipation of energy, of course, we can expect that our motion, our vibration, will decrease in time, but it will decrease in time quite slowly. If we increase the dissipation of energy, basically increasing the damping coefficient, we can expect that now the dissipation of energy will be much quicker. So the dissipation of the motion will happen in a lower time. In addition, we have for nonlinear structure also to use ductility, and we have already defined what ductility is. Mainly in earthquake engineering or in seismic engineering or in structural design, we can approximate or can define the ductility of a nonlinear structure as the ratio between the ultimate value of the displacement and the displacement at first yielding. Of course, when I have a spoon like this undergoing a very ductile deformation, after the applied force finishes, we have a very large permanent deformation. We would like to design our buildings in order to ensure them a behavior like a ductile behavior of a spoon under large forces. We don't want to design for a brittle behavior. So we would like to design a structure for a large value of the ductility. Okay, so now we are at 12:15, and so now it's the time to stopping the first part of our lecture. And I will transfer the hosting of the lecture to Dr. Ruccolo in a few minutes and after a small break. But before having this, since I've shown you some very interesting, in my opinion, I hope that you share this kind of opinion, very interesting movie, I would like to ask you if there are some questions about those movies or some questions about the seismic response of structure. Of course, my invitation is to use the internet addresses I will send to you in order to see again those movies. And since you have also the recording of the lecture, to make some personal reflection on this kind of reasoning. But before leaving the lecture, I would like to ask you if there is some curiosity about those movie and about the main parameters ruling the structure and seismic behavior of a structure. Okay, any questions from the audience? So when I increase the stiffness, which is the effect for natural frequencies, does it increase? If I'm going to increase the stiffness, the natural frequency will increase or not? Please reply. Okay, you will reply during the oral examination in few times. Okay, if there are no comments or questions from the audience, I would like to stop the recording or pause, just pause it.
Yes, I would.
What you prefer?
Stop, maybe.
Maybe stop. Okay, stop.